All right, welcome back to Statics 1. Today I want to give you a couple examples of the evaluation of moment vectors in a coplanar system. So what is a coplanar system? Coplanar systems is a system where all of our members that we're acting on, in other words, the beams or columns or whatever members we're acting on, they're all on the same plane, and the forces that are acting on them are also on that same plane. So the simplest thing is just to work on our XY plane. And we'll have Z, essentially, if we have a Z vector, it will be coming out of the board. This is moments. Here's what we're going to do today. Moments in coplanar systems. And remember, if we're in XY system, it's a Y. We're in an XY system, then the Z is going to be coming out of the board. We can know that by the right-hand rule. You take your hand like this to go from X to Y, it means Z is coming out of the board, okay? So we have a positive vector, positive Z vector, it's coming out of the board. So now we're going to talk about moments. And you remember that, I'll just review again, and you can skip over this if it's like not something you want to see again, because we've talked about this several times. We have a wrench. It's applying some moment or a torque on this bolt, and the moment that's applied is equal to the force times the perpendicular distance. So if we have a force acting like this, the perpendicular distance is the distance where, if we were to put in a right angle, it would go through that point. So that's our perpendicular distance, D, and the moment, the magnitude of the moment equals the force times that perpendicular distance. We also know that if we look at this from perspective, one other perspective, which is that if we know this distance, and that's R, be careful, that's not the perpendicular distance. You cannot say M equals F times that R length. But if we know that we have an angle theta here, then remember that M equals F times R sine theta, because sine theta is opposite over hypotenuse. So R is our hypotenuse. So we multiply the hypotenuse times the opposite of hypotenuse, we get the opposite, which is this D, the length of that D. Perpendicular distance. Remember that word, perpendicular distance. You can't just multiply by any distance between our force and the point at which you're evaluating the moment, which in this case is this point here. So that's typically like a point O where we're evaluating the moment. So if I had an O there, then I probably would put a little subscript over here. And these are magnitudes. And remember, a moment is a vector. Don't forget that. Moment is a vector. A moment is a vector. So the moment, you put a little arrow on top. In this case, is going to equal F times R times sine theta times, because we're in the XY plane, the moment is going to be in the direction perpendicular to that, which will be in the direction of our K vector. And in this case, we have I'm going to hold this end here where we're evaluating the moment, and we're pushing it this way. So we're turning this thing counterclockwise, which happens to be a positive moment. So we don't have to put a negative here. If I had the force coming in this direction, then we'd have a clockwise rotation, and I'd have to put a negative on that, applied to that vector. That's kind of a review where we're at. Now I'm going to erase this, and we'll go through another example. We'll go through a couple examples taken straight from the textbook. All right, so my first example is going to be the application of a force at the end of a beam. And the force, this beam, this is a wall. We have a beam attached here. And I'm going to call this point O. And I'm going to apply a force here of 100 newtons. And the distance is going to be 2 meters from the wall. Okay, so here's our force. I'm going to draw the line of action. I'll write that word down. So keep it in mind, line of action. And it applies to a force. It just means what is the line of action, a line that that force is acting on. So in this case, the force is acting on a line like this. And I'll just draw it, start way up here and just continue down here. So if we want the perpendicular distance, in this case, it's easy. Because the force, we're going to go to this, on the line of action, the perpendicular distance is right here. And it's actually that 2 meters because this is perpendicular. I'm going to do it in green so we can see it better. Put a little box here in green. See, that's perpendicular. So that's our perpendicular distance. So this one's easy. The magnitude of that moment equals the force times the distance. Perpendicular distance equals 100 newtons times 2 meters equals 200 Newton meters. And that's how you write it. Newton N dash M. 200 Newton meters. Okay? And don't forget, it's a vector. So let's think about, first of all, is it positive or negative? And in this case, again, I'm going to hold this end where we're evaluating. We're pushing down clockwise. Aha! So I need to apply a negative value here. Negative. So the answer is negative 200 Newton meters. And if you were to write this, that's the magnitude. If we were to write it as a moment, we'd say the moment equals negative 200 Newton meters times K, vector in the Z direction. Okay, that one was easy. Let's look at one more. Again, I'm going to draw my wall. In this case, I'm going to have my beam or pipe or wherever it is coming out of the wall like that. And I'm going to apply a force over here. All right, let me look at my example. My notes, I have, okay, so we have a 50 Newton force. We have 2 meters here. And we have 0.75 meters from here to here. 0.75 meters right here to the center of this thing. And my point O is right here. I'm going to call that point O. So we want to evaluate the moment caused by this vector at that location. Okay, so how do we find our perpendicular distance? Again, we're going to draw a line showing the line of action of the force. And I'll draw it right through here. That's my line of action. And now I find the perpendicular distance, which in this case is going to be right at that point. And I can draw, again, I'll draw my little box in green to show you that it's perpendicular, right? And now I'll just multiply it out. Well, we have, so the distance, we already have that distance here, 0.75 meters. So the moment here, I'll draw a line here so I can distinguish that's it, that problem. Here with this problem, this moment equals, or the magnitude of that moment, and I'll put a little subscript O. That implies the point. We're evaluating the moment about that point. Is equal to that 50 newtons times our 0.75 meter perpendicular distance. And is it positive or negative? So we need to think about this. Here we have, in this case, here's my point where I'm evaluating. I'm going to hold it, and I'm going to push this way. So you can see that this marker is rotating clockwise, negative, right? So that's a negative value. And then we can multiply this out. 3750. Is that right? 353, yeah. It's going to be equal to 37.5 Newton meters. And if we want to write it as a vector, negative, we need to put a negative here. And if we want to write it as a vector, it's going to be equal to negative 37.5 Newton meters times K. Right, because it's coming out of the board. It's a vector coming out of the board. Okay, I want to do one more problem. So what I'm going to do is I'm going to erase the board one more time and then do this last problem, and then we'll move on to, okay, I'm back, and we're talking about moments in coplanar systems, and I want to show you one more example. So in this case, we have a wall over here, and we have like I don't know what it is, piece of wood or something, or maybe it's a pipe or something. And we're going to be applying a force in this direction, force. We know that the length of this thing is R, right? Yeah, so we know that the length of this is R. Would it be correct to write moment equals force times R? No, it's not, because the force and the moment arm, which essentially this is like our wrench, are not perpendicular to each other, right? So you cannot do that. So what we need is the perpendicular distance, which essentially be from this point here upward, right? So how do we do that? Oh, and I have to give you one other piece of information. This angle here is theta, right? So now I'm going to draw my line of action, which seems to be always in blue. That's my line of action. Line of action. So that's where we're drawing our force. And now we find the perpendicular distance, which will be essentially from here straight down. And I'll draw my little green box to show that it's perpendicular. Now I'm going to draw my line here connecting these. And this has a length of, we're going to call that D, lowercase d. And we know is wrong, but we do know that the force times our perpendicular distance, that is in fact the magnitude. And this time we have it going, what direction is it going? Counterclockwise, right? So that's okay, it's going to be positive. So the magnitude of this moment about my point O, which I'm going to draw right here, this is point O. Magnitude of the moment about point O equals the force times distance. All right, we know that the sine of theta equals the opposite over the hypotenuse. So we're going to take the sine of theta, opposite over the hypotenuse, divide by the length of r, which is the hypotenuse. That will give us our d value. So I can write this equals F times R times sine theta, right? Where R sine theta is just equal to D in this case. And if I had values here, I do have values. I'm going to call this 100 Newton force. And I'm going to say that R equals 2 meters. And I'm going to say that theta equals 30 degrees. Now we know how to do this. We're going to put in here 100 newtons times 2 meters, right? 100 newtons times 2 meters times sine of 30 degrees. And it's a good thing to remember, one of the key trigonometric values, sine of 30 equals 1/2. So this is going to be equal 100, 200 times a half, 100 Newton meters. And again, it's because we're doing a counterclockwise rotation, it's going to have a positive value. So that's our moment, the magnitude of that moment. And if we want to write it as a vector, it's going to be equal to 100 Newton meters times K vector, because it's coming out of the board. If all the forces are in the XY plane, the moments are always going to be in the K direction, either positive K or negative K. All right, so that was the moments in a coplanar system. So we're going to talk next time about how to evaluate moments in a 3D system. And we're going to use what we learned before, which is a cross product, which it turns out that if you take the position vector, cross it with the force vector, you can get the moment evaluated about a point for any 3D system. Sounds complicated, but it's not so bad. And we'll talk about that next time. So that's it. See you in class. Send me any of your questions about lecture.